Hello everyone, I hope you are doing well. In this video, we are going to solve another problem related to variational method or variational principle. Let's see the problem statement and we will directly dive into the solution. The statement says use the variational method. In some books, it's principle. In some books, it's method. Both of them are equivalent terms. So use the variational method to estimate the ground state energy of the hydrogen atom. So what we have to do is to estimate the ground state energy of the hydrogen atom using the variational principle. So specifically we have to use this method, none other method but this method, to estimate the ground state energy of the hydrogen atom. Let me give you a really quick overview of this method. It's an estimated method or approximation method. It means that whatever results you get for the energies and wave functions of the system, the result is not 100% exact result, which means there could be some error in the result. Like we are estimating ground state energy, which means the result, for example, let the true value is 5.8, let there is some true value 5.8, and through variational method maybe we get 5.7. So there is some error from the true value. There is a possibility of some error from the true value, and the variational method is a approximated method. Here we get approximated results, and we can possibly get the exact results if we make a good guess about the wave function of the system under study. So let's quickly get started. First of all, we have to write a trial function for the ground state of the hydrogen atom. And from the experimental knowledge and the prerequisite knowledge we had from classical physics, we know something about the ground states of the hydrogen atom, so we can make some good guesses about its wave function. And what these guesses are, that the trial function, that the ground state wave function in hydrogen atom, for hydrogen atom, has no nodes. This is a really basic requirements that we are inserting on the hydrogen atom wave function, since the wave function of hydrogen atom is really straightforward and simple. So the ground state wave function in hydrogen atom has no nodes. It means it will never be zero anywhere except at infinity. The wave function will never be zero anywhere except at infinity. That is what no nodes mean, and that is what the ground state normally means, that it has no nodes. And the wave function should be normalized. It means it should vanish at infinity. Okay, it should vanish at infinity. These are only two things, two requirements that we had for the ground state wave function of the hydrogen atom. Okay, and they are really straightforward and easy. So let's write it. It should be normalized. It should be normalized, and for normalization we'll write a normalization constant in it. So psi naught, which shows it's a wave function for the ground state. Naught sign shows ground state. That is equals to a. A is the normalization constant multiplied by exponential negative alpha r. Okay, alpha, where a is the normalization constant. This a will ensure that the wave function is normalized. We'll calculate its value right now in the solution, because it's needed to be calculated. All the constants that we have introduced here needs to be calculated, and these constants include capital A and this alpha sign. Okay, so A is the normalization constant, alpha is the adjustable parameter. Alpha is adjustable parameter. R is better to write the position of electron from nucleus as center. All right, additionally there is no angular dependence of ground state wave function of hydrogen atom. That is why we have not introduced any angle theta or phi in it. Okay, that is something that we know from classical physics as well. That is why we haven't used any theta and phi here. We'll be using the spherical coordinates for its calculation. Okay, while in case of harmonic oscillator we used a Cartesian coordinate system like dx, dy and dz, but here we'll be using the spherical coordinate system like dr, d theta and d phi. Okay, they'll be used later on. So r here is the radius vector. Okay, r here is the radius vector and we'll be using that coordinate system. And you can see that this wave function has no nodes. It means if you put it equals to 0, it will be only equal to 0 at infinity, otherwise it will never be equal to 0. This wave function is only 0 at infinity. You can easily confirm that. Okay, if you put it equal to 0, having a node means that the wave function is 0 at some point other than infinity. Okay, that, and the number of nodes they are, which means the number of points at which it becomes 0. Okay, one node means there is one point other than infinity where the wave function becomes 0. Two nodes mean there are 2 points other than infinity where the wave function becomes 0. So you can confirm it. A is a constant, it will go right in the other side. Now this is a property of exponential function, that it is never equals to 0 except at infinity. Okay, except at infinity this function can never be equal to 0. You can confirm that easily using calculator, using different values and all. Yes, this is the simplest wave function that we can devise for the hydrogen atom. In some books what they use is this ratio. They use it like that. Both of them are equally valid. You can use a similar method and you'll get to the same result in both cases. Okay, I have used it this way. This is the trial function and that satisfies our really basic conditions. So now let's proceed with the problem. First of all, I'm gonna calculate the normalization constant so that we may know it, and then we'll use the variational method to estimate the ground state wave function. And knowing the normalization constant is important because it needs to be inserted in the energy expression as well. So let's first calculate the normalization constant. And we know that the normalization condition means that the scalar product is equals to 1. Okay, here we can put the value of psi, which is a e to the power minus alpha r. This is a and here a again. We can convert them into integral our volume. This is a volume integral and it means it will occur on the whole space. R, theta and phi, all of them will be involved here. Then we write the wave function from the bra vector. This is bra vector and this is the ket vector. The one in the bra vector, we find out its complex conjugate and then we write it. Okay, since there is no iota in here, that is why there will be no difference. If there would have been any iota here, for example, it would have been iota alpha r, then we have to find out its complex conjugate and then we'll have to put it right here. Okay, that is some additional information that you should know. So since there is no iota, we'll simply write it the way it is, like that, and then this wave function and then its volume integral, and that should be equals to 1. Now let's break that volume integral, and this a and a makes a squared. Since it's a constant, it's e to the power minus alpha r and it's e to the power minus alpha r. Bases are same, so the powers will be added. and in place of dv we write r square dr sine theta d theta d phi. Okay, this is dv in spherical coordinates. All right, dv in Cartesian coordinates is different. In Cartesian coordinates, dv is equals to dx, dy and dz. Okay, in spherical coordinates, it is equals to r square dr sine theta d theta and d phi. Alright, so you should know about it. In this example, we are using spherical coordinates, so all of them will be in spherical coordinates. Now here the limits of integration. For r, it will run from r is equals to 0 to infinity. For theta, it will run from 0 to pi, and for phi, it will run from 0 to 2 pi. Now next step is to write the integrands separately for each of the integral, because the variables are all separated. Here I write all the terms which have phi in it, only d phi. None of the other values are in phi, so it's like that. Then theta is equal to 0 to pi. We have sine theta d theta for it. And then we have r is equals to 0 to infinity. And for this we have r square and this e to the power minus 2 alpha r power is added, and dr is equals to 1. This angular stuff that has been introduced right here has nothing to do with the wave function that we have chosen. Okay, if you are asking me that how this angular dependence is coming, that's not angular dependence, that is just integration of our whole space on all angles, on all phi's and all. Okay, we can see the wave function is still radial dependent only. It doesn't have theta and phi, and that's what we mean by the angular dependence, that the wave function doesn't have theta and phi in it, nor the operators that we are applying on it. Okay, so let's solve it. Here we'll write a square. Okay, then we have d phi and integral. What would be its integration? Now you know that if we have this situation, its integration is simply x. Okay, if we have 1 in here, then its integration is simply this thing here. So similarly, the integration of this thing will be phi, and we'll write phi in place of this integration, and limit of integration are 0 to 2 pi, so we'll write them like that. Then we have sine theta. Integration of sine theta is minus cos theta. That is something that we already know, so we are just using it. It's minus cos theta, limit of integration from 0 to pi. Then we have this integral that I'll calculate separately, and we'll put its value right here. Okay, because I don't want to mess up everything. Let's calculate it separately, and we'll put it right into this equation, because that similar integral will be used for the energy calculation as well. So calculating it separately will enable us to insert the same value right there as well. We do not have to use or solve it again and again. So let us call it as equation number A. Okay, and calculate this integral. Okay, we'll use integration by parts, in which I'll take this term as first term and this as a second term. That is equals to first term as it is, integration of second term, negative sign by formula, integration derivative of first term and integration of second term, and integration of this whole term after solving it. Okay, and limit of integration from 0 to infinity. Oh, I can't write it here. It's dr and 0 to infinity as, let me write it again here. It's r square. Okay, so this is how it's gonna look like. We'll calculate it first, and we'll take integration of this term again. Okay, that is what we mean, and the limit of integration will be inserted at the end when all of it is simplified. Okay, so let's solve it. Integration of e to the power minus 2 alpha r is e to the power minus 2 alpha r as it is, divided by the derivative of its power, which is minus 2 alpha. Derivative of power is minus 2 alpha. You can easily calculate it. Then d by dr of r square, it is 2r. Derivative of r square is 2r. Here simply x is replaced by r. Okay, don't be confused. Here the integration of e to the power minus 2 alpha r is e to the power minus 2 alpha r divided by minus 2 alpha, and we have to take its integration, so like that. All of the terms in which we'll get r in it separately will become 0 at the end, so we will write them like that side by side to reduce the length of the terms that we are getting. This term will ultimately become 0 because of this r and this thing. Okay, so trust me, you can continue them if you want, but this term will become 0, and then we have this term left. This minus and minus becomes plus, and 1 over 2 alpha, this 2 and 2 cancels out as well, so 1 over alpha can be taken out of the integral, and we are left with e to the power minus 2 alpha r, 1 r as well, dr. Let's do its integration again by parts. 1 over alpha can be taken out, and integration by parts, its first term and its second term. So first term as it is, integration of second term, minus integration sign d by dr of first term, which is r, dot integration of second term. Again, since this term has r in it separately, it will become 0. Okay, only this term will be non-zero, so we'll take it 0 as well, and we'll neglect it. Next is 1 over alpha, negative sign, this negative sign, dr by dr is 1. Okay, so integration of this term we know is this, and we have another integration because it's a part of integration by parts. So 1 over alpha will come out, 1 over alpha square, minus minus become plus, and 2 also come out of the integral, and we are left with this thing. If you are confused about this integral, then the results that we are gonna get, you can remember it and insert it whenever you get this integral. That's another alternative you can do. Integration of this term is again, but you should know how to calculate various integrals because you can't remember all of them. 2 2s are 4, alpha cube, and it's alpha cube. Now we'll upper limit minus lower limit. Okay, so we'll put the upper limit, which is e to the power minus infinity. In place of r, we'll write infinity. Infinity will multiply with 2 alpha to become infinity as well. The negative sign needs to be mentioned. Okay, it's in power, and it needs to be mentioned. Minus alpha is not equals to plus alpha. Okay, when it's in power. Upper limit minus lower limit, we'll put 0 in place of r, so it's this. Plus 0 is equals to minus 0, so that is why I didn't write 0 here. 1 over 4 alpha cube, e to the power minus infinity is equals to 0. Okay, this is equals to 0 minus e to the power 0 is 1. So it's 0 minus 1 is minus 1, minus 1 becomes plus 1 over 4 alpha cube. This is the value of that integral. Which integral? This integral. Okay, and we'll use it later on as well, so write it separately so that we can use it after that. I'm writing it here. R square e to the power minus 2 alpha r dr r equals 0 to infinity, that is equals to 1 over 4 alpha cube. I'm gonna put this value right into this expression number a. Okay, and let's see what's gonna happen next. Okay, we'll simplify it and we'll calculate the value of the normalization constant from here. A square, here let us, okay, let me write it here and we'll put the limit of integration in next step. You can write here putting this integration value right into equation number a. So here we'll write 1 over 4 alpha cube as the value of this integration. Let's put the value of limit of integration in phi. In place of phi we'll write upper limit, which is 2 pi, minus lower limit, which is 0. Then we have this term, we can take negative sign out of this cos theta term, and upper limit minus lower limit. In place of theta we write pi, cos pi minus cos 0 degree, and 1 over 4 alpha cube, that is equals to 1, minus a square, this is 2 pi minus 0, which is 2 pi again, and cos pi is minus 1. Okay, pi means 180 degree, so cos of 180 degree is minus 1. So in place of cos pi we will write minus 1, minus cos 0 is 1. Then we have, this is minus 2 minus 1 minus 1 is minus 2, 1 over 4 alpha cube equals 1, and minus minus is plus, this is 2 2s are 4, 4 and 4 gets cancelled out, and a square pi by alpha cube equals 1, which means a square is equals to, taking these to the other side, alpha cube will be multiplied and pi will be divided here. This is the value of a square, and if you want to find the value of a, we'll take the power 1 over 2 on both sides, so alpha cube by pi whole power 1 by 2. This is the value of a, which is the normalization constant, and we'll use this value at the end of this solution. We'll simply put that value at the end of the solution, but we should know how to calculate it, but because in different cases this constant will be different, so we should know the basic equation, the basic product that will give us the normalization constant, and that basic product is this self product, scalar product between psi, that should be equals to 1. This is the normalization condition, and using this procedure that I showed you people, you can find out the normalization constant really easily. And if you calculate it separately, it becomes really easy for us to do the rest of the things, because we know one of the thing. And since we have calculated the normalization constant, now we can actually start the major process, which is the energy calculation process. And now the ground state energy could be calculated as follows. We have E naught. This means it's the calculation for ground state energy with naught sign, a small zero you can say, and we have this thing divided by using not to show that it's for ground state. Let us call it as equation number B. Alright, here H hat is the Hamiltonian for the hydrogen atom, and let us write it. Hamiltonian is Hamiltonian of hydrogen atom, and any system that we have has two type of energies. One is kinetic energy and another is the potential energy. So for kinetic energy we have this expression minus h squared by 2 m. M is the mass of electron. Since it's all about the single electron that the hydrogen atom has, del square plus the potential energy, and the potential energy the electron has with the nucleus will be negative because it's attractive. That is why we'll use minus e square by r, and I'm using k here, a symbol, because sometimes in some books they take it in atomic units and they take minus e square by r as the potential energy, because in that case the units are different. Okay, and in SI units we take k e square over r. K is actually 1 over 4 pi e naught. This is k. This is actually you can see k e square by r square. This is the Coulomb's law, Coulomb's force, and in terms of potential we have 1 r less, so in the denominator k e square by r. K means 1 over 4 pi e naught. So it's totally up to us whether we take k or not. It's just a constant. If in your example there is no k, then you can proceed later on eliminating k everywhere where I'm writing it. Okay, it's simple. You can eliminate k, but if it requires you to include k, so you can proceed the way I'm doing it. So it's really a matter of choice, and it doesn't bring any difference. So k e square by r, negative sign because it's attractive potential. This is actually the Hamiltonian of hydrogen atom. And in the denominator of B, this is equals to 1 since we have satisfied the normalization condition. So that would be equals to 1. Psi naught, we know that it is equals to what we have assumed and predicted at first place. H hat is this. So let's put all of these things right into equation number 4. Putting values in B, so we get this situation. Psi naught, let me write the Hamiltonian first. Okay, the denominator is equals to 1, so, and in later step we'll just continue with this single line. So let's simplify it. That is equals to, now at that stage I'll separate the product between the two. Let's separate the ket and bra vectors. Okay, this is the bra vector and this is the ket vector, and they are common to both of these quantities since they are being added to each other. Just like we have normal multiplications when we are taking something common and the thing that is inside will all share that thing that is outside which I just mean that this term is common to this term and this term, and this term is also common to this and this term. So we can simply separate them, and we can write as psi naught for this term first. We can take negative sign outside, so a cut square by 2m delta square, then psi naught this, then this negative sign, then again psi naught, and we'll write e square k by r in between and psi naught closing. Okay, doing so we can calculate both of these products separately. Okay, and simply put their values at the end. what we'll do is the same thing. We'll calculate them separately and we'll put them right into this expression. So let us call it as equation number C. All right, now let's calculate first this thing because it will be easy for us to do, and then we'll do this one. So first we'll calculate this. Okay, here k e square is a constant, so we can take it out, and inside is left like that. Now we can put the value of psi naught right here. Psi naught, what is psi naught? It was a. We'll use a here, we'll put its value at the end, okay, for simplification, because we otherwise we have to write the same thing again and again and again. It will be simplified just at the end. So a e to the power minus r alpha r or alpha, then we have 1 over r, then a e to the power minus alpha r again. Now let's write it in the form of integral. Then we have volume integral. This comes first with a conjugate over it, and since they are real number, they conjugate and this term remains the same, so we write it like that. Then 1 over r operator will be applied on a e to the power minus alpha r. Then the volume integral close. Okay, k e square, this becomes a square. We can take it out of the integral. Then we have 1 over r e to the power minus r alpha, and here 1 over r when applies on e to the power minus alpha r is, since 1 over r is the operator, this when applies on any phi, it results into 1 over r into phi. This is just like a position operator, so that is how it affects the psi. In case of differential operators like that, the situation becomes different. When applied, psi changes into another thing, but in case of these, psi remains the same. So, because here we always include operator, that is why I'm just mentioning you people, you should know these things. Then we have r in the denominator. In place of dv, I'm gonna write dv in spherical coordinates, which is r square dr sine theta d theta d phi. Limits of integration will be 3. Okay, we'll write them in next step. K e square a square. Let's write 0 to 2 pi d phi separately, then 0 to pi sine theta d theta separately, and then this integration 0 to infinity e to the power minus 2 alpha r. Base is same, so powers will be added. The 1 r will be cancelled out. Okay, so it's 1 r left here. Dr sine theta. Oh, it's dr only because we have they are written just before them. So we have this situation. Let's solve this integration and see what's the result. Okay, that is equals to k e square a square. Now we are familiar with these integrations, we can simply write them. In place of d phi, we will write phi, limits of integration from 0 to 2 pi. Then we have sine theta. In place of sine theta is minus cos theta, and limit of integration from 0 to pi. Let's apply integration by parts on this, or else we can calculate it in rough work and we'll put it back into this equation. Okay, let's integrate it here in rough work and then we'll put it back. It's minus 2 alpha r dr, and this is the first term and this is the second term. First term as it is, integration of second term. You will not write limit of integration here, you will write limit of integration as applied on the whole thing. Okay, you are not supposed to write them here individually, it is applied as a whole. So minus integration, then we have derivative of first term and integration of second term dr, and this whole is integrated, and then we have limit of integration from 0 to infinity. This one goes to 0, as I told earlier, because of r. When we put the upper limit, this thing becomes 0. When we put lower limit, this thing becomes 0. As a whole, this whole term becomes 0. That is why I have eradicated it. So writing this negative sign here, and integration dr by dr is 1. So 1 integration of this term, which is e to the power minus 2 alpha r divided by minus 2 alpha, and now integrating it again, and limit of integration 0 to infinity. This minus minus becomes plus 1 over 2 alpha, integrating it again, e to the power minus 2 alpha r minus 2 alpha. That is its integration, and then we have limit of integration. Oh, sorry. It's negative here because 1 over 4 alpha square with negative sign. Okay. Applying limit of integration e to the power minus 2 alpha into infinity minus e to the power 0 minus 1 over 4 alpha square. It's e to the power minus infinity, e to the power 0 is 1, e to the power minus infinity is 0. So 0 minus 1 results into minus 1. Minus 1 becomes plus 1. So we got 1 over 4 alpha square. Okay. In comparison, you can see when we had square here, rest of all the things the same, we got 4 alpha cube. So here when we had only r, we got 1 over 4 alpha square. Okay, you can find a resemblance in the form we got. So let us put it right into here. Here let's put the limit of integration. It's 2 pi upper limit minus lower limit, 2 pi minus 0, which is 2 pi minus 1. I'm taking it common, so we have cos pi minus cos 0. In place of that, we will write 1 over 4 alpha square, k e square capital A square 2 pi negative 1, cos pi is minus 1 minus cos 0 is 1, 1 over 4 alpha square, k e square capital A square minus 1, and it's minus 2 minus this 4 and 2 cancels out, minus minus cancel out, pi k e square a square pi by alpha squared. Okay, this is the value that we got so far. Here we can put the value of a square. Okay, this is the time to put the value of a square to simplify it further. Where are you, a square? Let me find it. Here is a, and a square is alpha cube by pi. We needed to put a square, so it's alpha cube by pi, k e square by alpha square pi. In place of a square, I'm gonna write what is alpha cube by pi. Pi cancels out, it's alpha square and it's alpha cube. Alpha square cancels and two of them cancel, so one alpha left, k e square alpha. This is the result for one part of integration that we have done. Okay, for this part. Now let's do it for the second part. This part is done. Now let's do this part, and I'm gonna call this thing, it's actually that is equals to k e square alpha. Okay, I'm gonna call it as d. Now let's calculate this one. Okay, let's do that. Let's write the second chunk, which is, I'm writing here including the negative sign. Okay, here I didn't include the negative sign, but here I'll take the negative sign because the formula absorbs it, including the negative sign. including this negative sign. Okay, by formula, this thing is equals to, since it's a lengthy term, that is why I think. Okay, so let's continue. That is equals to taking h get square by 2m outside. Okay, integration our 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 whole space. Then we have del psi star not dot product with del psi dv. That is really simple formula. The negative sign is absorbed in the process. Okay, so del square is here, h cut square by 2m is taken outside of the integral, then this integral comes in, and we have wrote them in this dot product, and it's really easy to calculate. This one will help us to yield the result really easily. So we'll use this formula. You can remember it. I hope you got the formula. Now let's use it. Here we need to calculate del psi first. Okay, del psi naught static is equals to del psi naught. The reason is there is no iota in here, so psi star will equals to psi naught, and simply they are equal to each other. Now we know that psi naught is equals to e to the power minus alpha r. Okay, and del is equals to partial by partial r unit vector. Here we can see that del is equals to partial by partial r unit vector, and we can also write it as d by dr r unit vector. Since psi is only dependent on r, so we can write the complete derivative or the partial derivative. They both are correct, so I'm going to use the partial derivative term, and or we can use the complete derivative term as well. They both are correct. Using the complete derivative will make more sense because it's r dependent only. So partial by partial r, putting the value of del, which is partial by partial r. Okay, r hat and psi is a e to the power minus alpha r. A is constant, r hat is constant, so taking it outside, partial by partial r will be applied on e to the power minus alpha r. So we are left with taking derivative of e to the power minus alpha r, which gives e to the power minus alpha r dot power of its derivative, which is minus alpha. It gives minus a alpha e to the power minus alpha r unit vector. This is the value of del psi naught. Also its value of del psi naught star. So we'll simply put that value right into this expression to get the value of this expression. Only simple simplification will result into the final form. So putting into above expression, we have h cut square over 2m volume integral. I write it in r, theta and phi again. So in place of this we'll write this minus a alpha e to the power minus alpha r unit vector dot product with minus a alpha e to the power minus alpha r unit vector. Then we have dv. In place of dv we'll write r square dr sine theta d theta d phi. Now we need to separate the integrals on theta, phi and r and see what we are gonna get. Okay, here we can see this a and a becomes a square, alpha and alpha becomes alpha square. We can take them outside of the integral. So with h cut square by 2m, here we can write a square alpha square minus minus becomes plus, and dot, since there is dot product, we will get the product of these two quantities, and r unit vectors will be removed in the process. So 0 to 2 pi d phi, 0 to pi sine theta. You can remember the results of them. Actually both of them combines to give 4 pi. This gives 2 pi, this gives 2, so it's 2 4 pi always. So we'll directly put this value because we have calculated it multiple times, and now we know the result. E to the power minus alpha r and e to the power minus alpha r, they multiply to become e to the power minus 2 alpha r because there are two of them. We have r unit vector, and dot product of r unit vector with r unit vector will give 1, so it's not needed to write. We have r square dr left. H square a square alpha square by 2m. In place of these two integrals we have 4 pi. Then in place of this integral we have 1 over 4 alpha cube, as we calculated before, and I told you people that we will be using it. It's r square and this thing, so 1 over 4 alpha cube. And in place of a square I'm gonna put its value, which is, since a square was equals to alpha cube by pi, probably, let me see, yes, it's alpha cube by pi. Let's put alpha cube by pi in place of a square. H square by 2m. We'll cancel out other terms later. In place of a square I'm gonna write alpha cube by pi. Now let's cancel out everything here. This this 4 and 4 gets cancelled out, pi and pi cancels out, alpha cube cancels out, and yes, none other thing will be cancelled. This is left so far. So this is the value of this whole thing, including the negative sign. So let's put all these values right back into equation number C. This is E. Now I'm gonna write it inside this thing. Okay, k square by alpha, its value, but negative sign was not included. Here the negative sign was included and it was equals to this term. We are very close to our final result. This is equals to, putting in C, so it's equal to h square alpha square by 2m. This value, no negative sign, because as I told you people that I included the negative sign in the process, and this negative sign was not included, so it's here. And k square alpha, this is the value so far, simplified form, and we are almost 2 steps away from the solution, from the final solution. Now we need to use the variational principle. We will use variational principle, in which what we do is to variation of E naught will be put in, would be made equal to 0. What it means is that we'll derivate it with respect to alpha and we'll put it equal to 0. So partial E by partial alpha is equals to 0. This is what I'm gonna do, and let's do this. Partial by partial alpha, E, what is E? H square alpha square over 2m minus k e square alpha is equals to 0. We'll calculate the value of alpha from this equation. Okay, so first derivate it with respect to alpha. H square by 2m is constant. Derivative of alpha square is 2 alpha. Simply minus k square is constant. Derivative of alpha is 1 equals to 0. Taking it to the other side of the equation, we get k square. 2 and 2 cancels out, and we are left with h square by m. Alpha is equals to k square. Taking m to the other side of equation, and this here as well, m comes here, h square in the denominator. So this is the value of alpha, k square m by h square. This is the value of alpha. Now to get the ground state energy, this is the value of alpha naught, we can say, where the E is minimum. This is the value of alpha where E is minimum. So I wrote alpha naught here. Okay, minimization of this energy E gives us the closest possible answer that we can get for the ground state of the hydrogen atom using this method. Okay, as I told you, this is an approximated method. So, and every result that we are getting is sensitive to the trial function we are choosing. So this method enables us to, so the minimization of that energy that was resulted from that trial function enables us to minimize the error in the energy, okay, given the trial function we are using. Using this principle, using this method, we try to get as close to the exact solution as possible under the influence of the trial function that we have chosen, under the limitation of the trial function we have chosen. If the trial function was the best choice, then this minimization process enables us to get the exact solution. Even if the trial function is not the best one, this method enables us to minimize the error in the final result. So it works for the both cases. Okay, for a given site, this minimizes the error. So let's put this alpha naught. Now we'll put this alpha naught in this equation. The result that we'll get is the ground state energy of the hydrogen atom using the variational method. Putting psi naught in this expression, we get h cut square by 2m. Then we have alpha square in place of alpha square. I'm gonna put alpha naught square minus ke square alpha naught. Let's put the value of alpha naught, ke square m by h cut square whole square minus ke square alpha naught is ke square m by h cut square. Let's simplify. H cut square over 2m, k square e to the power 4, m square taking square. Okay, so k and this k square e square means e4 1 m, so m h cut square. This is h cut square and this is h power 4, so it becomes h power 2. Then what else cancels out? 1m cancels out. We are left with k square e to the power 4 1m in the numerator, 2 h cut square in the denominator, k square e4m h cut square. Now let's take common all these variables. Here we are left with 1 over 2. I took all these things common. It's 1 over 2 here minus 1. 1 over 2 minus 1. It's equal to minus 1 over 2. Okay. So we get k square e4m by h cut square minus 1 over 2. And the ground state energy finally that we got is at alpha naught, which is actually the ground state energy, is equals to k square e4m by h cut square minus 1 over 2, taking minus here, m e4 by 2 h cut square k square. This is the ground state energy of hydrogen atom. This is actually the ground state, exact ground state energy for the hydrogen atom. It means psi trial was the exact ground state wave function. Okay, we can put the value of k square as well here, because there is a form that is really common. K is equals to 1 over 4 pi e naught now. So what is k square? It will be equals to 1 over 16 pi square e naught square. If you put the value of k square right into the equation, what you are gonna get is 1 over 16 pi square e naught square. 16 2s are 32, so it's me4 32 h cut square pi square e naught square with negative sign. This is the term that we also get from the Bohr theory for the ground state energy for the first orbit, as in accordance to the Bohr theory. So you can see this familiar term, and this is the term, and if in case the potential energy that you people have used is E square by R, so the result that you are gonna get is the one which doesn't include the k square term. So it will be simply me4 by 2 h cut square. Okay, just like in this book, you can see that they got this ground state energy me4 by 2 h cut square with negative sign. They have they included E square by R. You can see here E square by R, they included E square by R as the potential energy. That's the reason they included the negative sign. They just took it common. That's not relevant, but I'm saying that they didn't take k square by r, but they took e square by r. That is why they doesn't include k, but it's totally fine to use it or to not use it. Whatever your teacher follows or you wanna follow, you can choose it. They are all correct. Okay. So don't be confused, okay, whether to use k or not. If you are given a question in your exam, and it's totally up to you, it's totally your choice to use k, because if you are using k, then it means you are using the SI units and you are expressing all of the results in SI units. But if you are not using k, then it means you are using the atomic units. So it's totally fine. Whatever is comfortable for you and easy for you to follow it, and you can mention it. Do mention that what kind of units you are following in exam, for example, and there is no issue at all. Yeah, so let's continue with finding out the wave function for the ground state of the hydrogen atom and see what form it will get, because sometimes you are required to find out the ground state wave function as well. So let's continue and complete this problem completely. So let's continue. Equals to k e square m by h cut square, while a was equals to, this is the value of a, which is the normalization constant. And since we want to find out the ground state wave function just the way we did for the energy, what we did, we inserted the value of alpha naught and a right into the energy expression that we had, which gave us the best possible estimate for the ground state energy of the hydrogen atom. Similarly, for the best estimate of the ground state wave function of the hydrogen atom, what we have to do is to put the alpha naught in place of alpha in the trial wave function that we had at first place. So the trial wave function is, the trial wave function for the ground state of the hydrogen atom is, you can write it, that was equals to, in terms of alpha, it was equals to a e to the power minus alpha r. Okay, and estimated ground state wave function, the best estimate that we can make using the variational principle, is the estimated ground state wave function for the hydrogen atom is, it is obtained by putting alpha equals alpha naught in this expression, and also in a, since a is dependent upon alpha. So putting the value of a here as well, in place of alpha we will write alpha naught cube divided by pi power 1 by 2 whole power, this is the value of a, e to the power minus alpha naught r. Now if you have already seen the wave functions of hydrogen atom, then you must have seen that variable, or in other words we can say the constant. One, it was a second for you, but we know this symbol a naught, which is for the Bohr radius. This is equals to Bohr radius, and the hydrogen atom wave functions are normally expressed in terms of Bohr radius. Okay, so let me show you. Here you can see there is that involvement of a naught everywhere. You can easily see it here. All right, so we will also express our wave function, this wave function, in terms of a naught, and for that purpose the relation is really simple. Here a naught is equals to 1 over alpha naught. Okay, if you take the inverse of alpha naught, you will get the Bohr radius. Okay, the expression is similar. And so what we can do here is to replace a naught. We want to introduce a naught into this equation, so what we'll do is taking alpha naught here and a naught here to get the value of alpha naught in terms of a naught. Okay, now we'll put alpha naught equals to 1 over a naught everywhere here. Okay, so sine naught ground state wave function equals in place of alpha naught we'll write a naught. So alpha naught cube means taking cube on both sides, so alpha naught cube will be equals to 1 over a naught cube, so we can write it as 1 over a naught cube pi alongside e to the power minus, in place of alpha naught we'll write 1 over a naught, so it will become like that. And you can mention a naught is the Bohr radius, where a naught is the Bohr radius, and you can also write them by writing under roots. Since we can divide the under root above and below, under root of 1 is 1, so there is no need to write it, e to the power minus r over a naught. Okay, and similarly it will reduce to this form, under root 1 is 1, so under root a naught cube pi e to the power minus r over a naught. Okay, this is the ground state wave function for the hydrogen atom in terms of Bohr radius a naught, and we can obviously get the value of a naught, where a naught is equals to 1 over alpha naught is equals to 1 over alpha naught was equals to k e square m by h cut square. H cut square will move to the numerator, so it will become k e square m, and if you evaluate it, it is the Bohr radius, that is equals to 0.0529 nanometer. Okay, it's a constant, and yes, as you can see here, okay, the involvement of k right here, which is 4 pi e naught, it's in the numerator, it means it's 1 over k, as here as well 1 over k. Okay, because k was equals to 1 over 4 pi e naught. Just to confirm you that k is involved here, and yeah, this is it for that problem, and I hope you got it. Like, share and subscribe. Goodbye.